Hello, you're welcome back. All right, so we're gonna be looking at AC circuit components, okay? Alternating current circuit component. Now, of course, the alternating current circuit component we're gonna be looking at are passive component. So we're gonna discuss passive component. Of course, a passive component are simply components that act as a load in a circuit. Okay, they don't provide any form of amplification. They don't amplify voltage. Okay, so basically they form a load, or uh, anytime you supply voltage to them, okay, they will act as a load, okay, to that particular voltage. All right, so now under this component here, I have three of them that I will be discussing. We have the capacitor. This is the symbol of the capacitor. Of course, the parameter of a capacitor is capacitance by the symbol C. All right, capacitance of a capacitor. We have the inductor, which is served as a coil, okay, measured by its inductance. Then the third one is the resistor. Please pardon me, the resistor. Okay, resistor, which of course is measured by its resistance. Now, among these three components, okay, we're going to discuss them one after the other. Two of them, capacitor and inductor, is actually referred to as reactive component. Okay, so what they do is that they provide reactance to the flow of alternating current, while the resistor is known as a resistive component because it only provide resistance to the flow of alternating current. Okay, so the difference between the reactance and resistance is what you're going to discuss as we proceed. So let's start with the very first component, which of course is a capacitor. So let's see what happens whenever you connect an alternating current. Okay, so I'm starting with that of a capacitor circuit. Okay, so now if I happen to connect an alternating current source across a capacitor, okay, something will be noticed. Okay, let's say the capacitance is C. Now you're going to notice that the current flowing through the capacitor, okay, the current I, of course, the current is I, the voltage is V. Okay, the current flowing to the capacitor and the voltage across the capacitor will have a phase angle. They will have a phase difference. Remember, an alternating current always have okay, a phase. It's either the phase is from the origin, or of course, or it actually gonna give you have a phase angle that is not from the origin. The phase angle from the origin is zero. Okay, so now when a capacitor is actually connected across an alternating current, you discover that the current passing through the capacitor, okay, will always lag. The current will always, please pardon me, the current actually leads the voltage by the phase angle of 90 degrees. So the current will always be ahead of the voltage by the phase angle of 90 degrees. Okay, so what does that actually means? It simply means that the voltage will be lagging behind the current by 90 degrees. Okay, so invariably, if I should write the equation of the current, okay, which of course is I is equal to I maximum, then sine omega t, then invariably the voltage equation now will actually have a phase angle of 90 degrees minus 90 degrees because the voltage lagging. Okay, so the voltage across the capacitor is going to be equal to Vm then of sine omega t, then minus 90 degrees. And of course, I have to convert that 90 degrees to radians. That's going to be 90 all over 2. So this actually shows that the voltage is behind the current by 90 degrees in as much as that particular component, the cycle component, is a capacitor. So please take note of that. Okay, so there's going to be a lack of voltage, okay, from the that of the current. So because of that, we can now simply say that anytime a capacitor is being connected across an alternating current, okay, that capacitor does not actually provide resistance as resistor do, but rather the capacitor provides what is known as reactance, okay, to the flow of alternating current. So what you have, the capacitor will actually offer reactance, okay. So reactance of a capacitor, and the symbol for reactance is actually for capacitor is given as SC. So what is reactance? Reactance is simply the opposition, okay, the opposition to the flow of alternating current, opposition to AC, and the reactance, the capacitive reactance or the reactance of a capacitor is the opposition to the flow of AC, which of course is offered by a capacitor. Offered by a capacitor. So that is why I call it the reactance of the capacitor or capacitive reactance. Okay, so now we are going to actually establish an expression for it. So capacitive reactance XC is actually given by the formula 1 all over omega C. The opposition to the flow of alternating current by a capacitor SC is given as 1 all over omega C. Of course, you know what the omega actually represents, okay? Of course, in wave or in circular motion, you know very well that omega here, this symbol omega is the angular frequency, the angular frequency of the alternating current. And you know very well that angular frequency is given by the formula 2 pi f. Please take note of that. 2 pi f. Okay. So that being said, I can simply say that, okay, for capacitive reactance, the reactance of a capacitor is going to be equal to 1 all over angular frequency, which of course is 2 pi f, then multiplied by the capacitance C. So please take note of that. So I can call this formula number 1, okay, or I can give it any value. So let's look at a typical example. Let's look at a situation where you have an alternating current circuit, okay, made up of capacitor, and the capacitance is 2 microfarad, and the AC is of a frequency of 60 hertz. And the question is, evaluate the reactance of the capacitor XC. That is the question. So now let's look at that. So that means in that case, S is going to be equal to 1 all over 2 times pi. Pi is 3.14 multiplied by the frequency, which of course is 60 degrees. Okay, then times the capacitance, which is 2 times 10 raised to the power of minus 6. 2 times 10 raised to the power of minus 6. Okay, so let's get this over with. So this is gonna be equal to, if I use calculator to do this, they're gonna have 1 divided by bracket open, 2 times 3.14 times 60 times 2. Okay, then of course times 10 raised to the power of minus 6. Then I close my bracket. Okay, so I will end up, okay, I end up having 3 point, am I mistaken? Let me do that again. Okay, let me do that. I have 1 divided by bracket open, 2 times 3.14 times 60 times 2, bracket close. So this here I'll have 0.00132, 0.00132. Let's do this. 0.00132. Then of course times 10. If I take the 10 raised to the power minus 6 to the numerator, because 10 raised to the power 6. Okay, so and I'll multiply this now. I'm gonna have 1, 2. Okay, 1, 2. Let's multiply this by 1 million. 10 raised to the power 6 is 1 million. Okay, so the capacity of reactors is gonna be 1327 approximately, and of course it's measured in ohms because it's an opposition. Okay, so it's measured in ohms. Please take note of that. That is how we evaluate capacitive reactors. Okay, so let's go to the next component, which of course is the that of the inductor. Okay, so now in the case of an inductor, okay, so if we supply an alternating current across the inductor, you will notice in this case that this time around, it is the voltage. The voltage actually leads the current, and it's by 90 degrees, by the phase angle of 90 degrees. So that simply means that this time around, okay, the voltage is leading. Okay, so invariably, if the current is still, if the current is the equation of the current is I maximum then sine omega t, then the equation of the voltage is going to be equal to V maximum then sine, this time around, omega t then plus, not minus, okay, because voltage is leading, plus the first angle 90 degrees, which of course in radians is pi all over 2. So note the difference. For that of a capacitor, it was minus, but now in that of the inductor is plus. Okay, so the voltage is leading the current by plus. Okay, remember for the capacitor, the voltage is minus 90, but for inductor is plus 90. So please take note of that. So now the next thing we are going to be looking at, as usual, is the opposition to the flow of alternating current by the inductor, known as the inductive reactance. Okay, inductive reactance. Okay, so now this time around the symbol is gonna be XL. Okay, Now, inductive reactance is given by the formula 1 all over omega L. And already we know very well, please pardon me, not 1 all over, please pardon me. It's not reciprocal. Inductive reactance is given as omega L, okay? So since we already know that omega is 2 pi F, so that simply means that inductive reactance is going to be equal to 2 pi FL. Okay, so let's see a situation where the inductance here is 20 millihenry. Okay, okay, in an alternating current whose frequency is let's say 50 hertz, whose frequency is 50 hertz. So if I'm to evaluate the inductive reactance, okay, the inductive reactance is going to be equal to 2 pi 2 times 3.14 multiplied by the frequency 50, then times the inductance, which of course is 20 millihenry. 20 milli is 10 raised to the power of minus 3. Okay, so here we go. This is going to be 2 times 3.14 times 50 times 20. That's 6280. Then, of course, divided by 1000. So that's going to be 6.28 ohms. 6.28 ohms. So that is the inductive reactance of the inductor. So please take note of that. All right. So now we are going to finalize everything. Now we have gotten the data of capacitor, the the inductor. Let's look at the resistor. Okay, so as you notice, okay, for the resistor, of course, the symbol, I use the symbol R. When you connect a resistor across an alternating current source, the voltage, both voltage and current, okay, are in the same phase. So there's no lag, or lead, okay? No, the voltage and the current doesn't lag or lead. So there's simply phase angle. The phase angle between the voltage and the current is simply 0. There's no angle between it. So that is why a resistor does not provide, okay? A resistor can never give you any reactance. So a resistor can only provide resistance to an alternating current, okay? It can only provide resistance. So a resistor cannot give you any form of reactance. So reactance can only be found for that of the inductor and the capacitor. So now to combine the three components, okay, the three components and the opposition, we have what is known as the impedance. Impedance. Impedance by the symbol Z. Okay, the impedance of an alternating current circuit is that total opposition. The total opposition. Okay, after considering everything, all the components, total opposition to the alternating current. Total opposition to alternating current, AC. So which simply means that if we are dealing with impedance, okay, in the case of impedance, we might end up looking at an alternating current that has probably the three components, okay, connected in series. Let's say a situation where you have capacitor, inductor, then of course resistor, all connected in the same circuit. So capacitor C, inductor L, resistor R connected to an alternating current. So the total opposition that is actually created, that is offered by these three components is called impedance. Now, apart from the fact that you might have the three components connected at once, okay? Even if it is one component, it's still impedance, which simply means that if we are looking at just a capacitor without inductor and resistor, the impedance, okay, for that of a capacitor is going to be equal to, is the same as the capacitive reactance. That is for if the component is just that of a capacitor. Okay, so now if the component is just that of inductor, that means the impedance is gonna be the impedance of the inductor, which is same as the inductive reactance. This is for an inductor. Okay, so please take note of that. So invariably now, if three of them are actually connected, as it is shown in this diagram, so the impedance is going to be the algebraic sum or the vector sum, because all of them have angles. This one, the phase angle of the voltage is 0 for the resistor. The voltage doesn't have any phase angle with respect to the current. This one here, the inductor, the voltage has a phase angle of 90 degrees plus 90 degrees with respect to current. For the capacitor, okay, the voltage have an angle of minus 90 degrees with respect to current. So which invariably, so we, if we were going to actually combine these three components, okay, we will definitely need to draw a vector diagram for both the voltage and the impedance. Okay, so vector diagram. The vector diagram is something as the phase diagram. Okay, of course, you know, vector is actually this with direction. Okay, call it phasor diagram, vector or a phasor diagram. Now, let's look at the vector diagram of the voltage of an alternating current that has this alternating current circuit that has these three components. So the vector diagram of the voltage, if you want to draw it, know very well that we're going to have a vertical line that represents the phase angle of 90 degrees, remember, and of course we'll have the horizontal line, okay, that represents the phase angle of 0, right, because this is 90 degrees, right? So positive, negative, and of course positive. So for voltage, you know very well that for the resistor, the voltage across the resistor, let me use VR to represent that. The voltage across the resistor is VR, the voltage across the inductor is VL, and the voltage across the capacitor is VC. So remember what we already know. For the voltage for that of the resistor is always 0 with respect to the current. The voltage for that of the inductor is always plus 19 with respect to current, and the voltage for that of the capacitor is minus 30 with respect to the current. So I can actually draw that. So that means for the horizontal axis, this is the voltage of the resistor. For plus 90 degrees, this is going to be for the voltage of the inductor. And for the minus 90 degrees, this is the voltage of the capacitor. So which simply means that the total voltage combining these three voltage VR, VL, and VC gives me what is known as the VRMX. So the VRMX of that of the alternating current circuit that has this component, capacitor, inductor, and resistor, is gonna be the vector sum. Of course, you know what is vectors and how we sum vectors. Okay, in this regard, vectors perpendicular and vertical, right? Vectors horizontal and vertical, which of course is perpendicular. So the total voltage, the VRMX of the circuit, or the effective voltage. Remember, VRMS of a circuit is the effective voltage of the circuit, okay? Is going to be evaluated by, of course, Pythagoras theorem, all right? Remember, when we have vertical vector and horizontal vector, to find the resultant, we use Pythagoras theorem, if you can still remember. Okay, so the Pythagoras theorem of the vertical vector, and the vertical vector I have here is the positive inductor and the negative capacitor. Okay, so that's gonna give me VL minus VC. This is for the reactance. I have to find the difference between, because they're acting in opposite direction. VL minus VC all square. This is for the vertical, and because they're acting in opposite direction, that's why it's VL minus VC. Then plus the horizontal vector, which of course is the VR square. Okay, so this is how we actually evaluate the VRMX, the effective voltage of the alternating current. Okay, by adding the voltage of the capacitor, the inductor, and the resistor, right? So please take note of that. We can also do that for the impedance. Okay, we can also do that for the impedance. Remember, for you to get the impedance of a circuit from Ohm's law, you know very well that current impedance, which of course is the total opposition, okay, multiplied by the current, IR or IZ, please pardon me, okay, is going to be equal to the voltage, the effective voltage of the alternating current. Of course, the origin of this came from V is equal to IR. Okay, the origin of this. So, but in this case, the resistance now is the impedance. So that way, now for me to be able to get the impedance, okay, please, the current also will gonna be the current here is the effective current IRMX. Okay, the effective current IRMX. So the impedance of the alternating current can be evaluated if we already know the VRMX. Then we divide by the IRMX. That is one way of actually evaluating the impedance. Okay, if we know the effective voltage and the effective current, by the time we divide that together, will give me the impedance. Or better still, okay, we can still draw the phasor diagram of the impedance, phasor diagram of impedance. So how do we draw that? The same way we drew the actually the phasor diagram of the voltage. Okay, so here we are. So for the impedance Z, you know very well that the vertical will be for the inductive reactance. The positive vertical, the negative vertical is going to be for the capacitive reactance, while the horizontal still remain the resistors. Okay, so for you to get the impedance, okay, the total opposition, this is the opposition due to the inductor, this is the opposition due to the capacitor, this is the opposition due to the resistor. So the total opposition, which of course is the impedance, please pardon me, the impedance is going to be equal to the vector sum of this, which of course is giving us the XL minus XC. This is the reactance all square plus the resistance square. Okay, so I will actually implore you to go through this formula, and I'm very sure that by the time I apply them, it will actually make more sense. Okay, all right, so that is it for now. We're going to continue in the next video. See you in the next video. Thank you very much.